All right, so you're in the talk for the evolution of Postgres high availability. It's a long and sordid history, and I'll try to keep things as accurate as I can. If I make a mistake, don't feel afraid to heckle or correct me. I don't have a slide introducing myself because that would be gauche. But basically, my name is Sean Thomas. I'm the author of the second of the Postgres high availability cookbook. You may or may not have heard of that or needed it for any reason. But it's going to be changing soon. There's been a lot of, I guess, updates in the Postgres world that make a lot of the old sections of it irrelevant. And as things advance, well, we've got to kind of roll with the times. And that's what this talk's kind of all about. So how many people are familiar with these two terms here, RPO and RTO, right? They are the linchpins of high availability, mostly because it lets you define your terms. Like, what does it mean to be highly available? Well, what's RPO? How much of your data can you stand to lose at any one moment? That's basically your guarantees. And what's RTO? It's all about the nines. Those two things define how paranoid you need to be when you're building your stacks, right? The point that really matters here is decisions dictate architecture. You basically say, I want to build this thing. How should I build it? Well, what are my constraints? How many servers do I need? What do those servers need to look like? How far apart are they? What are my failover guarantees, and how much that is all set up? Oddly enough, a lot of your high availability stuff tends to build itself because once you apply all those restrictions, there's really not much else you can do. There's not a lot of wiggle room. So I actually tweeted this a couple days ago, maybe. We were talking about this talk, and we were like, "Well, what should we do with this? How do we? How did Postgres kind of gain its high availability functionality?" And I asked the question because I wanted to make sure I didn't miss anything, like I'd asked you guys before. Like, what was there before 8.0 kind of made it official? And Ian, the maintainer of Rep Manager and maybe of other notoriety within the Postgres community, he was just prayer, because without archive command sending the wall file somewhere, what was there? Right. A script that kind of cheats the system, not really reliable, not something I would want to depend on and stake my reputation and company on. Yeah, frequent PD dumps. So in the beginning, kind of back then, like we already had mentioned, we had dumps, lots of dumps, stuff like that, scripts, mirrors, whatever. The main thing that you probably saw happening around a lot was proprietary solutions of various description. If you've ever heard of a company called Sios, they had their Lifekeeper stuff, and various implementations existed between 2005 and 2010 that kind of popped up out of the need to create high availability. Disk mirroring was a good one because your database has been copied at the byte level. If it crashes, as long as that copy is still around, you can bring it back up. And of course, everyone likes DRBD, which popped up in 2005, roughly around the same time as 8.0. And that is distributed replicating block device. So it's networked disk mirroring, which is pretty handy. So this was the old way. Looks really piddly, doesn't it? You've got just some kind of floating thing, some syncs between your two databases, and really that's all you needed for high availability, right? This is like 2004, 2003 era, and nobody liked that, but it's all we had, or did it? So I'll get into this a little bit later. There actually were solutions back in 2003, 2004, 2005, but I don't like to bring them up. and you'll see why in a minute. So while shipping, it actually entered in Postgres 8. I did not know this. I actually started with Postgres, back in the 7.3, 7.4 days, but I quickly hated it and threw it away. I'm not going to joke about that. I totally was tired of the vacuuming and everything else, and I went straight to MySQL, and until I changed jobs, that was it. Postgres, I wrote it off entirely, much to my chagrin. But when 8.0 came out, Postgres started to kind of enter the real world of business use. People were starting to put hundreds of gigs on it, and then they were like, well, we need to protect this hundreds of gigs. And more so, it used to just be archive command. If there was a command defined, it would run it. If you didn't have one, it wouldn't run it. So archive mode was added a little bit later to formalize things, so it wasn't so, I guess, incidental. So while shipping made your high availability look kind of like this. You had your one database, your archive command would ship to some other location, and then you have to stand by consuming those walls. And that actually made a lot of people happy, because then you could have your remote high availability. You could have it on a different server, on a different network, on a different continent, but your data would be a lot easier to secure than like a disk mirror or some kind of slapdash solution that we'd had brought up before. In a high availability situation, it looks a little different, but not too much. And actually, this particular setup, you probably saw a lot. If you are familiar with Lifekeeper or Pacemaker or any of those solutions that kind of build this kind of stack, you'd have a couple of nodes in one data center with a disk mirror in between them, or maybe wall shipping, depending on how asynchronous they wanted to be. And then they'd have wall shipping between the two data centers. And then they'd have some kind of failover mechanism, like could be SIOS, could be Pacemaker, could be some script they wrote, could be keep alive D, whatever you want. That was the component that kind of coordinated this whole mess. And that was HA for a very, very long time. So what did this give us? Well, it was arbitrary. We could control the walls. We had the ability to move those walls around. They were our files. So we can send them or suck them from the other system. We can send them to a remote third party and then use that as a distribution mechanism to send to multiple replicas. And every node is theoretically, as long as it's consumed all the wall files, a perfect copy of your master database. So it made it great and convenient to do a lot of things. And your PR, your point-in-time recovery purposes, obvious effect that is built into Postgres. But what is not so great about it? Well, this is going to be a long-running theme in this presentation. No standby, or no hot standby, I should say. If you can't access your database, it is useless to you, completely worthless, except for crashes and stuff. So I think what I'd like to get to the point here is it's great for high availability and pretty much nothing else. We'll get to that, though. So to summarize all of this, it's great to have, we now have the backup copies that are convenient to create, and maintaining them is easy because we got the wall stream, the wall copies. Getting them online would be a great next step. This is where the evolution comes in. Triggers. Notice those dates. So trigger-based replication actually kind of came first. Sloaney's been around since 2004, oddly enough. So if you actually wanted to do your high availability in a way that you use trigger-based replication, where you copy your data using triggers inserts to a table to a new online target, you could do that. And as you can see from the dates of Londist and Picardo, there was a lot of desire for this kind of functionality. And that will get to our next point of evolution in a minute. Trigger-based replication works like this if you're not familiar with it. You've got like a table, maybe multiple tables, some kind of change log that they get inserted into based on the activity on those tables. And there's either some kind of daemon or a push system that sends those transmissions to subscribed servers, and then they integrate that into their own data. It's cumbersome. We'll get to those the wins and woes and whatever things in a minute. But in a high availability situation, it looks kind of like this. Notice how similar this chart looks like. The only difference is that middle line. Instead of the wall files being transferred, it's the trigger traffic. Not much difference otherwise, except the standby is online. And that's one of the reasons people were preferring triggers in this case, because they could say, oh, not only is this a copy of my database, in theory, as long as the trigger system is stable, but I can query it, and in some certain limited situations, even make modifications to that data on the standby. So it worked great for like reporting systems or things where you wanted to integrate multiple services, what have you. This is the thing we can learn from as far as what triggers give us. So what can triggers give us aside from walls? Unlike walls, they can span Postgres versions. They can copy more than just a few tables or your entire database. You can actually pick what you're copying. And that read replica is being able to have your hot standby is, I think, the most important part of this. Your nodes aren't just sitting around dead, because what you had before that, when it was just wall recovery, the Postgres nodes would actually be down, and they were in what we call continuous recovery. They would just read a wall file, recover it, read a wall file, recover it, wait for a wall file, read a wall file, and recover it. So this would be a slight evolution above that, even though it was kind of bolted on and unstable in a lot of ways. The main problems with triggers is they have a lot of drawbacks. That was only just the ones I could think of off the top of my head. There's dozens, honestly. And I think my favorite phrase back when I was using the most infamous, probably, Sloaney, is, oh great, Sloaney's broken again. We had a 1.4 terabyte database we were copying over with Sloaney to a reporting system. And I had to rebuild that several times because Sloaney would stop replicating, or it got some unrecoverable error, or I found a bug that I had to report upstream, or whatever. Triggers, because of their nature, are fragile. And the right amplification is not anything to sneeze at either, because instead of having one copy of your data written to your database, you have one copy, then one copy to the tracking table, and then both of those right to your wall, and then maybe any kind of accounting on top of that for every subscriber. So not the best solution, but sometimes it doesn't matter. Like if you don't have an OLTP system that does lots of transactions, maybe that doesn't matter. But what can we learn from triggers? It's important to know that triggers give us the freedom to have an online database that gives us partial copies. And it can span Postgres versions. These are three things that will lead to the next evolution point of how this is actually all working. And unfortunately, things kind of stopped there. Consider this was 2005 when we got wall shipping, and then nothing else for a while, and still a while. Boy, that timer sure keeps going. So 2010. So we had 5 years of basically nothing, from wall shipping to when we got wall streaming in Postgres 9. And the reason I like to point that out is because that was a huge improvement. That was a patch that everybody was waiting for, and I know for a fact that when I was working on these old 8.4, 8.3 databases, I actually wrote a big blog article on how to use PG Migrator before it was called PG Upgrade. And I knew that getting to 9 would be the best thing in my life because streaming replication and hot standby. So it works like this. Basically, you've got a process that kind of sits on top of the primary, and it sends to a receiver on each standby you create, and you can chain it. Not a big deal. How this modifies our high availability chart now is, I would say, significant. So notice, I've got an async line now between those two data centers. And my transfer mechanism isn't just transfer mechanism now. They've got names, pacemaker, rep manager, whatever you want to put there. Those all kind of grew up in the world of streaming replication because it made it so convenient. And then, of course, your proxy layers, those started to pop up too. PG Bouncer, HA Proxy, to some extent PG Pool, because it tried to do a lot more than just being a proxy. And this, I think, is actually when high availability in Postgres really kind of took off in 2010, roughly. So what do we get out of this? Our online readable standby and the lag. The lag, I think, is a really good win. Because think about it. Before, our lag was in 16 megabyte WAL files. And if you were missing a WAL file, or if you had a sync process that only pulled every minute, any WAL files I could find, your sync process was fragile to the point of missing, possibly thousands of transactions. Now, if your lag is low, you could be missing, orders of magnitude less than that. That is a huge, huge win. And then one of the reasons a lot of people use stuff like DRBD or disk mirrors or any kind of systems in their pacemaker failover clusters is because WAL files were just awful. They were great to get the actual functionality, but as far as high availability is concerned, it wasn't nearly good enough. Still, though, same shortcoming of WALs. We have to copy the whole instance. We can't just, do parts of the database. We got to copy the whole freaking thing. If you have a 20 terabyte database, guess what you're copying? And, version mixing, but that's kind of an obvious. So what can we learn from this, though? Well, we still want to have our partial copies. The standbys, they're readable since they're online and readable, but they're of limited utility. You can only select from them. You can't create any objects in the database. Like you can't use it for direct reporting. You actually have to chain it somehow. And the promotion process to actually make that standby usable requires a restart. That's not a zero-sum element because you have to disconnect all the existing connections. You've got to bring it back up, so that takes time. And if you're in a very time-sensitive situation where you want your nines, you can only be down for, what was it, 26 seconds a month or something. So, that 20 seconds it takes to do a promotion is relevant. So I probably should have had more Cricket slides because between 2010 and 2014, we also still had a lot of nothing. There was advancements like we added a couple of features to streaming replication. Like we made it so that you could, add synchronous, and there were a few other tweaks to it. But generally, it didn't really change much. But when 9.4 came out, dear Lord, this literally changes everything, and it changes it a lot, way more than I can even describe here because it makes Postgres something of a middleware supreme, I guess you could say. So we have the advancement of logical slots. Logical replication and slots. Slots are required by logical replication because we need to know where the slot last, processed data from the WAL, and we need to know which WALs to keep for each individual slot. And slots are basically just pointers to the WAL that say, keep this until I'm done using it. Well, based on this logical replication, we added, by we I mean second quadrant, added something called PG logical that reads that slot, decodes the actual data in it, and can send it to another PG logical node. And then, like triggers before it, and this is why I kind of brought up triggers earlier, like triggers before it, you could actually take that stream, take it apart, and use that to create more replicas like a trigger would. It can be version independent to a certain degree because you had to be 9.4 and above, but it can be version independent. You could only make partial copies. It's a huge, huge change. And then in Postgres 10, it got even further kind of built in. It actually became part of Postgres. So you could create a provider, subscriber, create your constellation of systems that are logically replicated, and every one of these nodes is online constantly. Constantly. You don't have to worry about promoting any of them. They're always available. You can write to them whenever you want. It looks like this. So I've got 3 tables in my provider over here. I've got my wall sender, and there's a little decoder object sitting on top of that. It sends to an apply process, and I'm, in this case, only copying over 2 tables. It's a very simple implementation of it, but it kind of shows you that we have the same kind of functionality of triggers using the built-in mechanisms of wall streaming. So we kind of get the best of both worlds in this case. And in replication, in high availability, it looks like this. This chart keeps coming back over and over again, doesn't it? Except with slight variations. Now, instead of having, async replication between the 2 data centers, I have logical replication between the 2 data centers. And why would I want that? Well, it lets me have my other data center online instead of having a system that I can switch to and then promote. My failover process is now, okay, PG bouncer HA proxy, just point to the new node, done. I don't have to promote anything. I don't have to change anything. The database is online. All I have to do is, keep the old one around if I want to do any kind of forensics on it later to make sure that I didn't lose any data. And there you go. That's, I wouldn't say it's the quintessential, final form of high availability, but it's getting closer. This is where we are now. Okay, this is where Postgres anyone who has a Postgres installation of any kind can build this if they want. So kind of what I reiterated before, having logical replication gives us a lot of power. We have our online writable copies. There's no trigger overhead, no promotion. You can span Postgres versions. Like, I could go on for like bullet point after bullet point, and for good reason. This is something that I actually kind of find slightly amusing, because MySQL has had their implementation was logical replication, and it never had they never had a physical streaming wall kind of setup like we did. So I always considered it fragile because it broke a lot. We were always having to rebuild MySQL nodes because for whatever reason the synchronization got broken, or whatever. Because it's their implementation is more of a statement-based decoding of the wall contents they have, and it's got its issues, but it's gone through a lot of changes, just like our replication systems have. So what do we not get with logical replication? Well, this is probably its shortest shortcoming, is that it's one way. And actually, at our booth earlier, we had someone that was interested in coming to this talk. They pointed at it and said, I'm interested in that bi-directional replication thing. We'll get to that in a minute. But the other issue is that lag is actually physically dangerous to your database. Remember when I brought up the slots, the replication slots? Well, those basically mean if your standby is down, or if there's lots of lag between the 2 servers, the primary is accumulating those logs, and you could physically run out of disk space. So when you're using logical replication, you have to monitor that closely, or you could die. And that's a lot harder to come back from, because when you run out of disk space, file syncs start to do weird things, and then you can't really guarantee the integrity of your database at a certain extent, and then you start getting corruption. Don't let that happen. And a lot of people don't know this about logical replication, but your data is not sent until the commit statement. So the decoding process is triggered by the commit statement, effectively. So if you have a transaction that takes an hour of just sending data to the wall and then commits at the very end, well, the standby is just sitting there waiting for the wall to pick back up. It's just sitting there going, where's my data? It stopped. Well, it's basically too much to swallow. It'll wait and it'll get it. It'll show up eventually, But for actually in Postgres 9.6, there I think it was 9.6.5 or 9.6.6 was a recent patch that we sent because the standby would get tired of waiting and it would shut down the connection because the wall was still being decoded. There was a timeout that we would like, okay, the timeout of 1 minute, it's set that to like 2 hours and it'll fix it, and it did. Basically, long transactions would get stuck in the in the process of being decoded. Because they were just a long transaction, and the connection gave up and went away. Well, as soon as you set that timeout to something longer, it fixed itself. That was the way to get around this bug until the new version came around and said, maybe I should monitor the socket and actually look for activity instead of just the actual stream keeping its update pointers going on. And that fixed that particular bug specifically. And conflict management, I say, because since you can actually write to the table locally on the systems, you may have data coming in that conflicts with data that's already there. And so you need a mechanism to make sure that doesn't derail the replication itself, like just totally shut it down. What does this give us, though? What is this next step of our evolution? Well, we can finally have our online upgrades because all the nodes are online. And also version independent as long as you're on 9.4 or higher. And it would be great if you could write from one node to the other and vice versa, right? Even if it were just like a ping pong fashion. Currently, if you have a provider, you can't switch the roles and have like provider and subscriber switch. So if you have there's a failover process, you basically have to rebuild the relationship. That's not entirely useful. So enter bidirectional replication. This is something that Second Quadrant is also working on. And we're working on this because somebody's got to, honestly. And this is how it works. Remember that previous slide where it was just that top part? Or sorry, was this the bottom part where we had the decoder and the wall sender and the apply stream? And that's how it worked? Well, now there's another one. We have two of those. And as an extension, it kind of sits in the middle and basically interjects any kind of necessary changes between the two streams to make sure that they merge properly. And that's really all BDR is. Honestly, any one of you could probably spend a couple hours, well, maybe more than a couple hours, but spend some time with your favorite programming language and write an extension that can sit on top of the wall streaming system, the logical wall decoders, and you could write this yourself. All it really does is it sits on top of the wall stream and lets each node write to the other nodes. But it can accept two streams is the main difference. This is what now remember that earlier high availability diagrams that I had that were the same over and over and over again. The same two nodes, same async link between the two data centers, the same pretty much everything except for the components here or there might change as the things kept evolving. Well, in BDR things change a little bit more because each node has to talk to each other unless you start getting away from mesh networks, and that enters a lot of theoretical ground I don't want to cover here. But basically all the nodes talk to each other because it's bidirectional replication. You can write to the primary you can write to node A, it'll write to node B. You can write to node D, it'll write to node C, and vice versa. And you basically you end up with a consistent cluster within your latency limits. That's the main difference. BDR1 does this, BDR2 does this, the upcoming BDR3 does this. They all do this. And basically it all goes back to this. It's one of these created multiple times over and over again with a management backend and a few other things that kind of make sure this all keeps running. So when you have that kind of setup that looks like this, that introduces a few problems. Actually, more than a few problems. It introduces lots of problems, lots of theoretical problems that can't easily be solved. First of all, are conflicts. I think we have a test suite where Gianni, if you know Gianni, Professor Gianni, that we have in Italy, he actually wrote a bunch of tests for this to find out what all the conflict scenarios are. There's a good couple dozen at least that we've covered just for 3 nodes. You can write to one node based on latency, get issues that pop up, and you need to have a mechanism in place to kind of resolve them, or you'll end up with a divergent cluster where some nodes have some data that's different from nodes on others. Everything has to be idempotent, or you don't have a cluster that's, I would say, even close to being ACID compliant. And I hate to say this, but it's still proprietary. BDR is something that we're developing and no one else really is, at least not yet. So if you want BDR, you kind of have to come to second quadrant to get it. And I hate saying that because I would have thought by now there would be like an open source community kind of thing, and we are rolling that in. Like, we're developing this, we're getting clients on it, and then we're trying to get the patches back to Postgres, just like we did with PG Logical, getting logical replication in core. But you would think something with this simple, someone would have sat down and done it themselves. They would have made this, right? But actually, there's a lot more work in there than you thought. There's tens of thousands of lines of code in our system. The other thing is PAC-ELK. I call it PAC-ELK. I don't know what the actual pronunciation is. If you're familiar with the CAP theorem, so a little guy named Daniel Abadi, he came up with this quote when he was blogging about the CAP theorem. CAP. So availability or partition tolerance is basically how it kind of boils down to, and consistency. So in that kind of setup, when you have a partitioned cluster like we do when you have a database that has multiple nodes like this that can all kind of write to each other, ACID basically goes away. Because an ACID system would normally prefer consistency. Well, if you have consistency, your latency is going to suffer horribly. You can't beat the laws of physics. Once you have 2 nodes that are separated by some kind of distance, any kind of latency will introduce issues of correcting any possible divergence, any kind of conflicts. That has to all be resolved. Well, as soon as you start doing that, do you really have ACID? So you've got to decide what you want to give up. And in the case of BDR, we kind of gave up a little bit of consistency to get that latency. The preference for low latency. Because low latency is always, wouldn't say always better, but it's certainly better than multiple round trips to each node as you're doing various algorithms for convergence and voting and trying to decide what data is always going to be the data you integrate. So the elephant in the room is that if we want low latency, we're going to get conflicts. There's lots of ways to resolve those conflicts. BDR by default uses last update wins, but when you do that, well, you're going to have a really good clock sync between all those nodes to make sure that one node isn't just always ahead of all the others and always winning all of the runoffs, right? So we're trying to find ways around that, but again, this isn't as easy as it looks. You'd think it's just 2 logical nodes writing to each other, but there's a whole lot more involved. I tried bike shedding it myself. Yeah, I'm totally wrong. That slide where it's just the two directional things, that's what it is in theory. I really wish Petter was here because he's actually writing a lot of the code, and he's had a lot of conversations with me, which I would say 80% of it goes over my head, but that 20% that doesn't, I'm like, oh, that's why. That's why this is taking so long to get working. And as I mentioned before, real consistency is abysmally slow. You've got to have your voting members. They all have to converge to an answer if you really want to have your ACID back. If you want to keep your ACID, you've got to make sure that no rogue transactions get through. So you need either a transaction manager or you need some kind of voting mechanism to kind of keep everything in place. Is there a middle ground, though? Kinda. So if you value latency, you get your instant gratification. Like your commits are just right away. But after that commit, it has to transfer that data to all the other nodes, right? And then that clock sync becomes a problem. Well, there are also some conflicts that you can't resolve. That's the dirty little secret to this whole thing. My favorite example for this is, so you have a node that does an insert, and the application, for whatever reason, the node crashes or gets disconnected. The application says, oh, I lost my transaction. I'm just going to retransmit to wherever I got reconnected to. Well, if you have globally unique IDs, which you should when you have a system like this, because then you don't have value 1 being inserted on both systems. Well, you get value 1 here and value 2 here, but it's the same data. But it's not a conflict because your IDs are different. This is where someone who likes to advocate natural keys will step in and go, ha! That's what you get for using surrogate keys. And they're right to a certain respect. But it also means that your application has to be aware of this kind of organization and architecture. You can't just throw any application on top of a bidirectional replication system and expect it to work. And, you know, there's updates. Say you're updating a call equals column plus 1. Well, all the nodes just did that. And they all did it simultaneously. So now, instead of adding 3 or 4 to your data, each node adding 1, you've added 1 4 times, and they've all transmitted that same interaction, and you've incremented your credit by $100 instead of $400, and that means you've just lost data. Well, there are ways to get around this, kinda. Usually, what we say is switch to a ledger system, so you're actually just doing a credit of 100, credit of 100, credit of 100, and at the end, you summarize it somewhere else in a view. But there's also conflict-resistant data types, which we're trying to work in that'll effectually kind of take care of this for you. They act as an accumulator automatically in the column. But again, your application has to be aware of this. You can't just expect it to work. That's the main key here. If you want multi-master, you're going to have to make some concessions. Now here's the real fun part. If you want consistency, say you have an application that can theoretically never lose data or have any kind of conflict resolved in a way that's, I would say, uncouth. Well, you're going to have either a global transaction manager or a distributed consensus model. One of the two. You can't get away from that. And the global transaction manager is going to be a throttle. So if you have a highly OLTP system, it's going to, however fast your global transaction manager is, that's basically how fast that your system can operate now. And if you're distributed over hundreds of miles geographically, that can be a problem. Your node in Helsinki is going to be a lot slower than your node in Texas if your global transaction manager is in LA. That's just how things are going to work. And the same applies to the global consensus model. If every node has to look at the transactions to make sure that no other transaction conflicts in some way, well, that's even worse, right? Every transaction has to go to a statistically relevant portion of the voting populace. So n over 2 plus 1 nodes have to get that transaction and say, okay, for every transaction. That's so much overhead that we actually for BDR 1 and 2, we didn't even look at it. We're just like, we're not going to put consistent, model in BDR at all. It's just not going to happen. We're kind of walking that back a little bit for BDR 3, but the point is, it's so ugly, we expect no customers to ever use it or ask for it. But it's good to have just in case. There's always that weird edge case where someone wants to really, Who cares if it's 100 times slower than it could be otherwise? I want that, integrity. And that's just how it works. The question is, can we get past these? Can we decide which things we want to integrate? And the clients out there that want to put this in their high availability systems, what things do they want to choose instead of, say, latency, or they want to prefer latency like we do? If someone wants to write, say, competitor to BDR, how will they do it? How will you do it? How will your application kind of evolve to be the next layer of multi-master? So like I said, BDR focuses on low latency, and it uses what we call lock consensus for DDL. We don't actually send the DDL to each node and have them fight over which one gets to apply it. We ask the consensus model, can I get a lock? And they say yes or no. And then we just apply the DDL locally and then replicate it. It's a very simple system. Other projects may decide differently. Maybe they want to have the global consensus model for everything. But it's slow. Like just the DDL stuff that I'm talking about, and that's just a lock. That's not anything else. That takes 2 or 3 seconds on a 4-node system, at least currently. So at least as long as there's only a few people working on it, PAC-ELK will live on. It's the limitation, I'd say, to getting to that next level past just regular logical replication to getting a truly distributed database model where every Postgres node can write to every other Postgres node worry-free. So I guess that's where the evolution kind of stops for now, because it's kind of we've hit what I would call the how I need to coin a term here. The PAC-ELK limit. I don't know. So that's pretty much the journey we've kind of gone through. This, I would say, is the endpoint from here. Maybe you disagree with me. It's possible. In fact, it's highly likely in a room full of database guys and application devs and of various description. Maybe there's some kind of cool new theorem I'm not aware of. That's fine. But as far as the Postgres world, how we've kind of gotten to this point where we have logical replication, and that kind of almost gets us to multiple master. This is the situation we're in. The question is, can we get past this? And what does that actually mean? Like, how do we actually get past PAC-ELK, or how do we integrate it to kind of take those concessions and change them into global user configs, for instance? We're like, okay, well, I don't care about this much consistency. Like, give me this consistency model and it'll be okay. Like, I know it'll make me like 40% slower, but that's okay. It's not 500% slower. But we need to quantify all that stuff. So, but anyway, that's been kind of my experience with this. I hope you kind of got what you wanted out of the long and sordid history of Postgres high availability into what I consider the quintessential element of this, because in this model here, you can replace any of those nodes. So say if those are all 9.6, I can just put a 10 in there. I can put a node 10 in there, and there, and there, and there, and suddenly I'm a 10 cluster and I never went down. So it's an exciting world that we're in right now if you want to pay the kind of the upfront costs of getting your application that can sit on that without falling apart. The question is, can we get to the point where your application won't fall apart without having to like make a bunch of changes on it? Changing to ledger inserts, for instance, would be a huge change to most apps out there. Like they just want to be able to do an insert or a update sum or whatever. So that's it. I'll take any questions I have time for. You were first. All right, so I actually don't know the answer to that. The question was, if we have two transactions that start at T1 and T2, T1 being before T2, and T2 commits before T1, what is the actual order that the subscriber sees? I would have to talk to the devs to actually get the real answer to that, but It all depends on the decoding, because from what I have been told, the commit time is actually what decides when it gets transmitted by the decoder to the accepting node. So, but they also have like transaction ID locks, or sorry, transaction ID numbers that in the LSN that they actually have to honor as well. So there is a certain amount of transaction reordering going on, but I'm not sure how much. Or, because they're not going to keep every transaction in that little window reordering it before it gets applied in the subscriber. But my guess is that's why the other reason we have the conflict resolution system built in, because in cases like that where you've got unordered inserts, you still want to have the idempotent result. We haven't had issues with it, so I'm assuming it works. I just can't give you the answer as exactly how. What kind of applications are using BDR? Okay, so since I actually work support on occasion, I actually know a lot of these companies that are using it. We've got a couple of companies that are banking applications. We've got a couple that are just regular front-end web stuff. And I've got one that's a basically online quiz system that's used countrywide for basic testing services, and they're having me convert their cluster to BDR. And they're using it effectively as a, I want to say, load balancing system. So they have regional nodes that can write to their local regions, which is actually what BDR was designed for. You write to your local region, and then since you're not doing a lot of data where Texas writes to California's data, for instance, then you don't have any conflicts. The data just kind of merges together. So there's lots of different use cases for it where it's not really a problem, where you have to worry about kind of the things I'd mentioned before, in which case this kind of thing is probably fine. You just write to your local node and don't worry about the merge conflicts because there won't be any. It's kind of getting around the issue. We also recommend something like sticky sessions, so that you don't have to worry about one application writing data to two different nodes simultaneously and expecting results to be in sync at certain points, and then you get an update waiting for an insert that hasn't arrived yet, for instance. But I mean, there's lots of caveats to kind of getting this stuff to work. But the customers that are using it seem happy with it. We've had the usual support call where like, well, our BDR cluster stopped syncing. Once we fix that issue, they don't worry about it. They say thank you, and then they kind of keep using the app. Unfortunately, I don't have numbers or like exactly which clients are using it. I'm not allowed to say exactly. So, Hetty, were you going to say something? Yeah, it's. Yeah, so the statement from the heckler down here is that are people really, do they know what they're doing when they're giving up the ACID compliance of having an ACID compliant database? Because by definition, if we go by the whole PAC-ELK system, a partition database such that you have multi-master in place literally cannot be ACID unless you have these heavyweight systems in place to kind of put it back on. Well, in my opinion, as a DBA that kind of learned their way into this, because I never actually took any database courses, while I was actually in college, I would say, as an ACID compliant database, we're going into multi-master. We're getting dangerously close to stuff like React, stuff like MongoDB that kind of give that distribution functionality but lose ACID, and then we always make fun of them. But here's the thing. You're consistent within the nodes you have. You're kind of ACID with a bolt-on caveat of your communication protocols may introduce inconsistencies. As long as you know what those inconsistencies are and you can correct for them, you're probably fine. But that's the caveat there. You have to actually know what those inconsistencies might be. You have to build the conflict resolution mechanism that you need to actually make sure that your data is idempotent, and then you have to take it for granted, and then hope it's all working properly. And that's what your tests are for. But your edge cases are always going to be there, and that's always going to be a potential source of, I guess you could call it potential issues, if you want to downplay it. Yeah. Yeah, so redefining ACID, kind of like how CAP became PAC-ELK, thanks to Professor Daniel Abadi. It's an interesting theory, but that also means someone has to go back to the drawing board and say, okay, how can we redefine ACID in such a way that it doesn't lose its, would it become ACID-ELK, acid else latency or consistency? Like, it's a theoretical framework that's actually completely worthy of someone's PhD thesis, I'd say. But it's not a simple thing that we can solve in the Postgres community.
Want to give away acidity too soon because they see nothing that extended latency, and especially even in like we work in finances and many people work in finances, and acidity was invented to support financial databases, and like I heard from lots of developers that the business stakeholders have no idea what they're asking for and what's going on. So it's not like we can solve it, but I just wanted to make a point that we need to raise awareness.
All right, so I just looked at the time, and I don't want to take any useful time from my compatriot here who wants to start his Where's My Byte presentation. But if you have more questions, catch me either at the Second Quadrant booth, or I'll be back here kind of watching to see where my byte went. And I'll be happy to answer your questions either here or upstairs. Bring your friends, bring your family, bring things to throw at me if I don't give you the answer you want. I don't care. But yeah, it was great talking to you, and I'll see you guys later.